Today's homework is focused on AR tracking and 3D reconstruction. The first thing we tackled was the camera calibration. Using the calibration's helper script, we took pictures of the checkerboard using the capture images function. Once these images were collected, we calibrated our camera using the calibrate camera function, which reads all the images in the directory, detects corners, and calibrates the camera. We save this as a file which will be used later. In part 2, we create the AR image pose tracker. This takes the reference image, retrieves their key points and descriptors using Brisk, and visualizes key points on the reference image. The feature matcher BF Matcher is set up to match key points. In the main loop, a video capture session starts. For each frame of the video, the frame is undistorted using our camera calibration data. Key points and descriptors are computed from the current frame, and the match points are normalized to compute the homography between reference image and current frame. The pose of the camera is computed in respect to the reference image. If the pose estimation is successful, a 3D cube is rendered onto the current frame using the computed pose. In part 3, we attempt to tackle the mobile phone 3D reconstruction task. Once again, we calibrated our mobile device camera. We collected multiple photos of our reference image next to a box object on the screen. Using AR image tracker template, we computed the pose of our camera in relation to the reference image. This time, we load these images individually rather than using video footage. As we can see, it's successful since an AR marker renders on the image. The relative rotation and translations are accumulated in lists. With every photo, we display the rendered cube and the matches between the first image and each subsequent image. Features are detected and stored as current key points and current descriptors. The epipolar constraint filter function is used to remove bad matches with the features. It does this by calculating the essential matrix for each match point pair. It normalizes points and applies the epipolar constraint. If it satisfies the constraint, it marks it as an inlier. After processing all images, feature tracks that are present in less than 4 images are filtered out. We compute the depth for all features with at least 3 observations. A matrix M is built and decomposed using single-value decomposition to compute the depths. Using the valid features and depths, we compute the 3D positions of the features. We create a point cloud from these 3D positions. Although the results are not accurate, there are 2 clusters.